Hi everyone, it's so good to be with you. And of course today what we're going to do is we're going to investigate probability in a little bit more detail. Here we are going to take the rules of probability that we've gone over already, and we're going to extend our knowledge by applying them to different situations. In a way, we're preparing ourselves for what might come up in a test or exam. But that's not the important thing. The important thing is that you've got a good picture of what the terms mean and how to apply. So let's not waste any more time. Let's make sure that we're on track. And so the first thing what we're going to do is we remember that we've got our concept map, which deals with the key ideas. Now, for learning about probability or anything in maths, remember mathematics is a learning subject. Don't let anybody fool you. There are certain things that you're going to need to learn, and amongst those are things like your definitions. And so when we talk about theoretical probability, you must know how to define theoretical probability. You need to make sure you know what the sample space, what the word complement means, how to deal with two events, and what the difference between mutually exclusive and events that are not mutually exclusive. Where does the word intersection apply and where does the word union apply? What rules are we going to do? So make sure that you've got these key big building blocks in place so that when you do a question, you can relate back to them and you can pick up the key terminology that will help you get the right answer. So let's just do a quick review of what the important factors are. So remember, we've done this lots of times. The sample space represented S. We say that the probability of the sample space is 1. That relative frequency is what we do when we do an experiment. It might not give us the theoretical outcome that we were predicting with probability, but if we do enough of them, if we make this very big, then we will get close. These two will get closer and closer to each other if we do lots and lots of trials. We recognize the word complement means that if that's the symbol for complement, it means it's not part of X. So the number in the complement is the number in the sample space minus those in X, and the probability of calculating the complement is 1 minus the probability of X. Recognize we can show this in terms of the Venn diagram, the blue area representing the complement of X. Remember the idea of union. Union is the bigger thing that we're talking about. It gives us less conditions. The outcomes can either be in one set, X, or in set Y, or Z, or whatever one you want to talk about. But they can be in either one of them. It's not very strict. It's a bigger amount, even though we use the word or. Whereas intersection is a much more defined process, and it's smaller, it's stricter. So, for example, you're going to say that 2 conditions are required. You can be somebody with blue eyes and somebody that is taller than 1 meter. That is a smaller group of people than if we were to consider the whole sample set. So even though we use the word and, remember it's limiting. It's very important that this word and, you recognize it's not opening things up, but it limits, it adds more conditions. Very, very important. When we have mutually exclusive events, these are events that cannot happen at the same time. So you can't be in a situation where you have, for example, a card that you're doing with playing cards, and you say, I'm wanting a card that is a heart and it's black. Well, sorry, that doesn't exist. Okay? You can't have a black heart. Sorry. Even if you are really cross with somebody, don't have a black heart. Have a cheerful heart, and it will go a long way. So mutually exclusive events are things that can't happen together. There's no intersection between them. So we recognize for mutually exclusive events, when we're calculating the union of mutually exclusive events, remember union means or, we can take the probability of one plus the probability of the other. And that's our or rule for mutually exclusive events. But if we are going to deal, and we've illustrated them like that, if we're going to deal with things that are not mutually exclusive, that means there's something in the intersection. Then we're going to say the or here is going to have an added part, and it's this subtract the intersection. Now, why do we have to subtract the intersection? Well, because there's a contribution to the intersection from set X and from set Y, and yet we consider the intersection as only being one thing. So we've got to take away the intersection when we're adding those two other bits together. So in this part, we're only going to count the intersection once. We count once for the intersection, but here you're counting twice. There's part of the element in the intersection there and there. That's why you've got to take away the intersection units. So there we go. We recognize in things that are not mutually exclusive, there are going to be elements here. And so they belong to X, they belong in X, but recognize they also belong in Z. And so we can double count them. In the intersection, we don't double count them, and so that's why we apply the OR rule. Right, I think it's time to take all of those rules, which are really cool rules, and apply them to some problems. Let's have a look at this particular one, which is one of my favorite dilemmas. And I'm sure you might struggle with it every now and again as well. Which decision should I make? Should I purchase a particular vehicle or a particular item or another item? Well, Bongani's in that situation. He's going car shopping. He's decided on the model. We're not going to say what model it is. Let's just say it's a really nice car. We don't want to give the owners of the car or the brand of the car any free advertising, but it's a really nice car. But Bongani can't make up his mind whether he wants the red one or the blue one. They both look really nice, but he's got to make a decision. So he's trying to decide, and he's narrowed down his choice to a red car or a blue car. He can only buy one car though. Most of us, it takes a long time to buy a car. Better to save, and then you can buy it for cash. Not many of us have that discipline. But Bongani can buy one car. Recognize it. It's either a red car or a blue car. Now they tell us some details here. There's a probability, a 58% probability that he'll buy the red car, and there's a different probability of buying the blue car. So how these statisticians came up with these probabilities, I don't know, but maybe they measured some things and they came up with these numbers. Let's just leave that those are the numbers that we've got to work with. And we've got to answer some questions about Bongani and his purchases. So, what's the first question? And the first question is, what is the probability of Bongani choosing the red car? Of not choosing the red car? Oh, I thought we were given a gift there, because we were already told what it was for choosing the red car. We were told what the percentage is, but what's the probability of not choosing the red car? Well, do you remember what rule we're going to adopt here? Well, it must be the complement rule. Remember what the complement is. All of those things that are not in the set that we're looking at. So we're going to ask ourselves, what is the complement of the red car? So if we say P not red, then what we've got to recognize is, first of all, the probability of red we've been given was 58%. We've been given that. That's up there. But what is not red? Well, that's going to be 1 minus the probability of the sample. Sorry, not the probability of the sample, the probability of the red. The 1 stands for the probability of the sample. So we're going to recognize of not choosing the red car. There are certain things that he can do. He can probability of the sample minus the probability of the red, which is 58%. And if we do that, we recognize this is the probability of red dash, okay, not red. We're going to say 1 minus 58. Now, if we want to do this correctly, we're going to say 58 is actually 0.58. And when we do the subtraction, I think you can see that this is going to be 0.42. Okay, 0.42, which turns out to be 42%. Now, that is the probability of not red. Not getting red is higher than the blue. We'll have to think about that. What might those probabilities include? But I hope you can see how we've applied the complement rule. Let's move on to the next question. So what is the probability of Bongani choosing either the red car or the blue car? Well, let's have a look. Now, recognize that the red car and the blue car are not overlapping. So these are mutually exclusive. You can't have a car that is red half of it and blue the other half. So we can apply our rule of the OR function here, the probability of either choosing red or blue is going to be the probability of red plus the probability of blue. And if you do that, it's not difficult to see that we're going to add these two together. 58% plus 38%, and I think that you can see that comes to 96%. So there's a 96% of him choosing either the red or the blue. Well, what do you think that difference of 4% can be? Well, let's have a look at our next question. And here is the next question. It says, what is the probability of not choosing either the red car or the blue car? We recognize we've almost got the answer, and we've established already that the probability of choosing red union blue was going to be 96%. So the probability of him not choosing, not red or blue, is going to be 1 minus the probability of red blue. And if you do that, you'll see that that is going to be 1 minus 96, or 0.96, which gives you 0.4, which is 4%. So, guys, what does this mean? Well, it means there's a 4% chance that after all his dilemma, Bongani is going to walk away and not buy either of those cars. Maybe his partner will twist his arm and say, Bongani, I think you can just carry on using your old car for now. Don't buy the red car or the blue car. 4% chance of Bongani not purchasing any car at all. Well, that was an interesting idea, and it hopefully helps you to calculate both theoretical probability and apply the complement rule. And we've also revised a little bit about the OR rule for mutually exclusive events. So I think we've ticked a couple of boxes in applying the rules. Let's take a break. We'll be back to apply some more rules after this. Welcome back, everyone. We're into investigating probability, and we've a number of rules of probability we're applying those to different situations. So here's a particular example of a question that deals with Venn diagrams and representing things on Venn diagrams. And I think it's a really nice question. So let's have a look at it. So here we go. Zama High School offers 2 sporting activities. Let's make sure that we can just highlight some information. The sporting activities, you can either choose to do netball or hockey. So they have 2 of those. It's not an exclusive choice. You don't have to do one or the other, but they offer the netball and hockey for you to be able to play. There are 600 learners in the school, and it's interesting that 372 of them have chosen to play hockey, while 288 learners, 288, they've decided to play netball. There are 56 learners that they've said, no, we don't want to play any sport. Maybe they've got some medical conditions, or maybe they just feel that they would rather play chess or do some academic activity. We recognize that there are some learners that play both hockey and netball, and we're representing them with X. And so the question is, given this information, draw a Venn diagram that represents all the information in terms of X. That's a really nice question. And I love the Venn diagrams because it helps us to see what's going on. It's a visual representation of data that is presented in lists of numbers. Here we've got the opportunity to draw a Venn diagram that can help us very clearly analyze and see what's going on. So let's get straight to it. So the first point that we are going to do is to recognize that we've got a sample space. And in the sample space, which I'm going to call S, we recognize that there are 600 learners. So the number of learners in the sample space is 600. And that's going to be very important for us in terms of our calculations. Now, let's deal with those that play hockey first of all. 372 learners play hockey. Now, we've got a set that represents those that play hockey. What we've got to be careful about is when we write that 372, where should it go? Have a look what I'm talking about. You see, the hockey ones are the ones that, I recognize I've created a B and an N. Let's call this should be H. So we're going to call this one the H. Sorry about that. H for hockey. I wondered why it was B, but there we go. The H set, they are the ones that are playing hockey. Can I put 372 here? Guys, does that make sense? Can I put 372? What do you think? Now remember, the 372 is everybody that plays hockey. We can't put 372 in that part because we recognize there's a middle part here that is involved in playing both hockey and netball. So I must subtract from this part the X. So it's 372 minus X. They are the people that only play hockey. They don't play hockey and netball. So in the same way, I can put the 288 over here, but I can't say that's all of the 208. I've got to subtract X over there as well. So in this respect, I recognize there's my Venn diagram. In terms of X, there were 56 that didn't play any sport, but those that only play hockey are 372 minus X, only play netball, 288 minus X, and the X are those that happen to do both. Hope you can see that this particular diagram immediately tells us that there's a chance that we can decide, are these mutually exclusive or not? Well, I guess the first thing we're going to have to do is to try and work out what x is. Remember, if it's mutually exclusive, then x will equal 0. But it's time to look at the next question, which asks us just that fact. It says, calculate the value of x. Now, without too much ado, it's going to be easier to do it over here. What do we recognize? We recognize that if we take all of these bits and add them together, we take that bit plus the x plus that bit plus the 56, that has to add up to 600. So let's go to that, and I'm just going to create some space for me to do that, and hopefully we'll get it. There's the space that we're going to do. We're going to say that we've got 600, and we know that 600 is equal to the 56 that don't play any sport, plus the x that plays both sports, plus the 372 minus x, plus the 288 minus x. Now, immediately you can see that those cancel out, and I guess that what we're going to do is we're going to solve for x. So I'm going to take x onto this side, and I'm going to say x is equal to 56 plus 372 plus 288, and over here I'm going to say minus 600. Now let's get the calculator out. Right, here we've got the calculator. Let's enter some data. So we go 56 plus 372, well, I'm saying it the wrong way around, plus 288 minus 600. And that will give us a value of 116. So we know now that x sitting over here in the intersection is 116. That tells us that there are 116 learners that play both basketball and hockey. Isn't that cool? Very good participation from those learners at Zama High School. Now, let's have another look at our next question. So, the question is are the events playing hockey and playing netball, are they mutually exclusive? And we're asked to justify your answer. Justify is an interesting English word. It simply means give a reason. Explain why you say so. Explain your thinking. And it must be a good reason that relates to one of the rules that has been established, one of the definitions that has been established. So let's get into it. Are they mutually exclusive? Well, if you look at the sets over here, you'll see that we've got the numbers clearly represented in terms of those that play hockey and netball. And what do we recognize? We recognize a calculation for the intersection. We've found the intersection of the number of learners that are going to play hockey intersection basketball or netball. Sorry, I'm saying basketball, netball. That's why it's getting all mixed up and the writing is all over the place. It's in the intersection. Notice it's 116. This tells us that the intersection is not 0. Remember, the definition for mutually exclusive events or sets is that the intersection must be 0. In other words, in that school, you could either play netball or you could play hockey, and there would be nobody in the intersection. So the answer is, Are these events mutually exclusive? The answer is no. And the reason why is that there are 116 learners that do both, that play both. They're in the intersection. The intersection is not equal to 0. In other words, you can, in a season, you can play netball and hockey at the same time during the season. Not obviously at the same time on a Saturday, but maybe you could play hockey on a Wednesday and you could play netball on a Saturday. That would be up to the way the calendar is arranged and the way that the sport is organized in the school. Let's do another question on the same situation or the same scenario. And so the scenario is this: what is the probability of selecting a learner randomly who plays netball and hockey? So we know that there are 116 of these learners, and we want to know what is the probability of selecting them at random. So imagine we've got 600 learners and we want to know what the probability is. There's more than one way of doing this. So let's go and see how we can do it. And it's often useful to compare the ways of doing it. So given the Venn diagram here, and given the situation that we've got, we can recognize the probability of choosing the hockey and the netball, the intersection of those two. We recognize the intersection of those two is going to be the number in the intersection divided by the number in the sample. And so it's not difficult to see that this is going to be 116 divided by 600, which was the total number. So if we take a look at the calculator, we can say it's the 116 divided by 600, and you can see that that gives you a percentage of 19.33%. So that's equal, if we multiply by 100, that's going to be equal to 19.33%. That's the probability based on these numbers. We recognize, however, that this isn't the only way to check what the probability in the intersection is. We can use the OR rule, and that's not too difficult either. So let's apply it. What we'd recognize is if we take the union of these ones, we'd recognize that's equal to the probability of the hockey plus the probability of the netball minus the probability of the union, of the intersection at least. So if we look at what's the intersection of the union of all of them together, do you see that it's all of these values together? So what we're going to simply say, it's that probability of those numbers. So it's the probability of those, which is, let's just get the calculator so we are clear what those values are. And I'm going to clear that. We've got it over here. 256 plus 116 plus 172. And this will give us the total in the union. It's all of those that are playing some sort of sport. So the probability here will simply be the total number, 544 divided by 600. And this one is the number that are playing hockey. Now, if we go back to our readings over here, we recognize that there are 372 that play hockey, and we're applying the 372 out of 600. And then those that played netball, do you remember what that was? Well, it's over here. They've given it to us. It's 288. So 288 divided by 600. And minus those in the intersection, well, we're going to have to make sure that we subtract the probability of 116 divided by 600. Now, guys, if you do that, you will find that, in fact, sorry, I just want to correct something here. Just use the eraser. We were wanting to find what the union was. So if you do those calculations, you will find that that is true, that you will find that they're equal to each other. So this is the union here, that this value of 119 will be the same as if you add all of those together and you solve for it. Okay, guys, I hope you can see that you can use the OR rule here by applying it to a situation and confirm your results. That's what I love about these probability rules. There's not just one way to do it, there's more than one way to do it, and you will get the same answer whichever way you choose. Let's take a short break, and we'll be back to explore some more problems in which we can apply the rules of probability. Hi everyone, it's good to be with you again. We've been applying those cool rules of probability to some interesting situations. Well, I hope you found them interesting, and we've got a few more scenarios to look at. So let's get straight into it. Remember to revise all the probability rules, and then you'll be familiar with how to apply them, because the problems can look different. But if you know the rules and you keep yourself on an even footing and don't panic, you'll be able to answer any question. Let's have a look at this one. So applying our concept map, we recognize we've got a situation here where there's a survey that's conducted amongst a particular sample of boys and girls. And we recognize within the survey there are 100 boys and 60 girls. So immediately, before I've even thought about looking at the data, I'm going to recognize that the size of the sample is going to be 100 plus 60, which is 160. So it now tells me that this information is being tabulated in the data, and there it is. Nice table. These are the boys, these are the females, and these are the ones that watch TV during examinations. Well, I hope they did watch TV because they were trying to learn a little bit more. There's always stuff on various channels that is going to help you with your exams. So please make sure you're one of those that tunes in. These are the ones that didn't watch TV during the exams. So we recognize that they didn't watch TV. The total sample, that's the number in the sample, is 160. So what are we asked to do? We recognize there's some missing information, and we need to find what the values of A and B are. Well, I think that isn't too difficult, but let's approach this problem quite logically, because we have to look at what information we've been given and what information we have to find. So let's have another look at it, and I've got some space here for us to do just that. So the first thing I recognize, which is a very important factor, is that in here is the total. And I recognize the totals add up both down and across. So if I were to take the number of females and I say 12 plus 48, that will give me a total of 60. So there are 60 girls in the experiment, and I know that's true. I also know that I was told that there were 100 boys. So I can recognize that 80 plus A will give me 100. So it's not too much of a stretch to recognize that in terms of this, I need to recognize that A is going to be 20. But what about B? Well, you can see that if we say 20 plus 12, that gives us 32. It confirms for us that we're right. But what about B? If we add up going down, we can recognize it's 80 plus 40. 80 plus 40 is 120. So this, I think, should be 128. Let's make absolutely sure, because when you're doing one of these tables, you need to make sure that things add up going down and across. So does it? 128 plus 32, or plus 30, plus 2 will give you 130, plus 30, yes, it gives you 160. So it does add up. This number of 128 for B is correct, and the number of 20 for A is correct. Now guys, you might not have been expecting this sort of problem in a probability question. It's really just a logic question. And you just need to be able to practice finding out about these equations and setting them up and recognizing that the sums of the rows and the sums of the columns have to come out, and they have to all equal each other and equal the final total at the end. Very good. Let's now move on to the probability questions, which are quite interesting. It says, are the events being male and did not watch TV mutually exclusive? Now, before we go and dive in and look at the data and try and work out what's happening here, there are many ways to answer this problem. Let's remind ourselves, what does mutually exclusive mean? It means that you can't do those two options at the same time. So in this case, the question was being male, and the other one was did not watch TV. So you can't be male and watch TV at the same time. But let's look at the data. Did not watch TV, by the way. So if these are all the male situations, there's the males that did watch TV. These are the males that did not watch TV. In other words, it's the set of 20 that did not watch TV even though they were male, and they were out of the total of 100. So I hope you can see that being male and did not watch TV, there are 20 young men who did not watch TV. Now, if those two sets were mutually exclusive, what could you predict? Well, they can't happen at the same time. That means they've got to be empty. The intersection between them has to be empty. There have to be 0 in them. But here we see there are 20 in them. So these are not mutually exclusive events. So the answer is, are they mutually exclusive? And the answer is no, because what we can say, the intersection of maleness and not TV, that intersection is the number in that intersection is equal to 20, and therefore it's not equal to 0. If they were mutually exclusive, those two sets would not intersect. So suppose if you're looking at this, you might say to yourself, well, maybe it could be a way of drawing a Venn diagram to be absolutely certain. And maybe that will be helpful in our next problem, in solving the next problem. But let's have a look and see where we're at. So here we go. Let's look at the next question. Said, if a learner who participated in the survey is chosen at random, what is the probability that that learner watched TV during the exams? So I think my idea of taking my 160 learners, and let's just divide them into two categories. Into the category that watched TV and those that didn't watch TV. So if we do that, we'd recognize that in this category here, the number B, we had 128 of them. So this is those that watched TV. So these are the TV, and this is the ones that did no TV. And we recognize there were 32 of those. We recognize there were 128 of those. So there are two ways of calculating the probability of those that did not watch TV. And the easy way, the straightforward way, is to count up those that did not watch TV, and we'll simply say the following. We'll say the probability of those that did not watch TV, no TV, is going to be equal to the total number of learners in the survey, which is 160, divided by those that didn't watch TV. And if we use the calculator, we will find, let's use the calculator to find the probability there. We're wanting 32 divided by 160, and that's equal to 1/5, 1 in 5, or 20%, 0.2. So I'm going to write it as a percentage, and we're going to say that is equal to equal to 20%. So that's one way of doing that calculation. Is there another one? Of course, we can use the complement rule. Because if you look at this, you can see 128 watched TV in the sample space. Those that were not part of those that watched TV are in the complement. Not watching TV is a complement of those that watch TV. So let's work out what the probability is of those that watch TV. And we're going to say that the probability of those that did TV is going to be 128 out of 160. And again, if we use the calculator, we're going to say the following. 128 divided by 160, 128 divided by 160 equals 4/5, 80%, and we're going to write it down there, 80%. And the reason I'm doing that is I want to use the complement rule, which says that P, no TV, or the complement of TV, is equal to 1 minus P of TV. And I hope you can see that's 1 minus 80%, which is, in fact, the 20%. And so we've got two answers using two different methods, and they both agree. Isn't that exciting? We've got the right answer. Okay, let's move on. So if a learner participates in the survey, what is the probability that the learner is not male and did not watch TV during the exams? Now guys, this not and an can be so confusing, but really it's not difficult. So let's be very clear about it. If it's not male, then it's female. And if it's not watch TV, then what we're asking is what's the probability of those females that did watch TV. So not male means female, and not watch TV, the opposite of that, not watch TV, is watch TV. So what we're wanting is the complement. And it's important that we look at that word that says and. Very important. So the opposite or the conjugate of this or the complement of this is watch TV. So what we're really asking is we recognize we're not worried about them, that they're not male. So we're worried about the females. So we're worried about these ones. And if we looked at this, the females that did not watch TV. So the females that did not watch TV are those ones there. So these are not male, and they did not watch TV. It's 12 of them, and we've isolated them exactly. So the probability of those that are not male, in other words female, and that did not watch TV, no TV, we'll recognize that that probability is going to be 12 out of the 160. And so if you do use the calculator again, we recognize we've got 12 divided by 160. We'll get a percentage, convert it to a decimal, 0.075. That gives us 7.5%. 7.5%. Good. I hope you can see how using the table and using our rules can help us confirm our answers. I hope you can go and do this using the complement as well. But let's quickly recap the rules that are so important that we don't make a mistake with them. So the rules that we've covered today are, first of all, what the sample space is, remembering that the sample space, the probability of the sample space is 1, what the relative frequency is, and you can get asked questions about that, the important rule for calculating complement. Make sure you're familiar with that. And then the difference between union being or and intersection being and, recognizing what mutually exclusive is and applying the or rule. This is the or rule for mutually exclusive. And then for those that are not mutually exclusive, recognize that there are elements in the intersection, and we have this longer rule where we subtract those elements in the intersection because we don't want to count the elements in A and B or X and Z twice. So we've got to subtract them from the intersection. Well, guys, I hope that makes a lot of sense. I hope it gives you confidence that when you're facing a question on probability, there's a very good probability that you're going to get the answers correct. In fact, I hope the probability is 1. From me, goodbye.